Where do you want to start?
It doesn't matter to me.
Yeah. At the top is usually a pretty good place. All right. There's a couple of key formulas that you have to remember about arithmetic and geometric sequences. One is, what is the nth term for an arithmetic sequence? You know what it is? The general equation? It's the first term plus the common difference times the number of terms minus 1. Okay? And the geometric equivalent is the nth term is the first term times the common ratio raised to the nth minus 1 power. And one way to think about this is arithmetic sequences are always, every term is adding the same common difference, right?
Yeah.
And geometric sequences, every term is a ratio, a common ratio of the previous term. And so with the geometric, we're going to take it to the n minus 1 power. Exponentiation being 1 greater than multiplication. Over here, we're multiplying the common difference times n minus 1, even though the sequence is adding every term. Now, let's talk about this one on the right first. Arithmetic tend to be a little easier to think about than geometric. Well, first of all, tell me which of these is which. The one on the left is what kind, and the one on the right is what kind?
The left is geometric and the right is arithmetic.
So let's do the one on the right. Tell me what the nth term would be.
-8 plus 10 times n minus 1.
And then that can be simplified, always, or almost always. So it's -8 plus 10n minus 10, which is minus 18 plus 10n. So that's the nth term of that. And that is what they mean by explicit, is always in this form, where it's a function of the first term, essentially. Now, the recursive is a word that is, we're going to define the nth term in terms of the nth minus 1 term. Okay? Instead of defining it in terms of the first term, we're going to let it be something with regards to the previous term. That's what n minus 1 means. In other words, if that's the third term, the second term is 2. So if a sub 3 was 12, a sub 2 is 2. So that's what we mean by n minus 1. Now, what do I have to do to give the recursive? Clearly, the nth term is not equal to the previous term, but what is it equal to? The previous term plus the common difference. Always. Every term up here is equal to the previous term plus 10. So that's the general equation for an arithmetic recursive formula. And then specifically, it's 10. So there is the recursive nth term, there is the explicit nth term. Okay? Now, let's go over here and look at the geometric sequence. Tell me what the specific geometric sequence nth term is.
2 times 4 to the n minus 1.
Good. And what about the recursive? If I want to make it related to the previous term, what's it going to be?
4n minus
4
1.
times an minus 1. In other words, whatever the previous term is, we're going to multiply it by 4 and get the next term. So coming up with the recursive usually has very little to do with coming up with the explicit. It's a little easier to come up with the recursive, but it's not nearly as helpful. In other words, if I gave you the recursive formula and I said, what is the 7th term of that sequence, it's not going to help you very much because you don't know what the 6th term is. Or if I was using some really big numbers, let's say I wanted to know the 200th term of this particular geometric sequence. Well, this would help a lot. Whoops, I didn't mean to erase that. The explicit definition would help a lot. I just substitute 200 for n and I got an answer. But the recursive wouldn't help much at all because I don't know what the 199th term is. So telling me that the 200th term is equal to 4 times the 199th term doesn't do a lot of good. There are some places in higher mathematics where the recursive formula tends to be used. Really higher mathematics though. I'm not sure exactly why they even teach you the recursive formula at this level. It certainly exists, but it's not that useful. All right, let's go on. An exponential function looks like this. Okay, almost always. At least if an exponential function of the form a times b to the x. That's what they mean by an exponential function. Okay? And usually if b is greater than 1, then it looks like this. If b is between 0 and 1, then it starts big and gets little. But for the moment, we'll assume that b is greater than 1. Now they give us 2 points. They give us a point right there, 3, 29, and they give us another point up here, 7, 215. So how am I going to figure out what A and B are? Because that's what we've got to do. In other words, they want an answer like y equals 2 times 3 to the x power. This is the kind of answer they're looking for. Write an exponential function, an exact one that goes through those 2 points. Okay? So that's our goal. The goal basically is to solve for A and B. So how can I do that?
You make 2 equations.
Give me one of them.
29 equals AB to the 3rd.
What's another one?
215 equals AB to the 7th.
Now, how do I solve this for A and B? I got two equations and two variables, so I know I should be able to solve it. Tell me how to do it.
Take 215 divided by 29.
So you're basically going to divide one equation by the other to get rid of A? You know, I'm not sure you can do that. I know you can add equations. I know you can subtract equations. I'm not so sure you can multiply equations. We'll see. If I said to you 2 is equal to 4 over 2, and I also said 3 is equal to 6 over 2, can I multiply those two equations? I get 6 equals 24 over 4. Yeah, I can. Okay. Maybe you can multiply or divide equations, and that might be the easiest way to solve this. However, when you're solving equations, think substitution or elimination. Why don't I solve the first equation for A? A equals 29 divided by B cubed. And I'll solve the second equation for A. A equals 215 divided by B to the 7th. And it's the same A, so now I can let that equal that, and I no longer have two variables. I got 29 over B cubed equals 215 over B to the 7th. And basically, we're going to end up doing what you probably wanted to do in the first place, which is 215 divided by 29 was going to be equal to B to the 7th divided by B to the 3rd. In other words, you did. You took that second equation and you divided it by the first one. And when we did that, we got this. Only it took me a lot longer to get there. So I like that you divided the two equations. And now, what is, you got a calculator? What's 215 divided by 29?
7.4.
Now take the fourth root of that to solve for B.
1.65.
So B equals 1.65. And now I go up to my simplest equation, cube that. So I got 29 divided by B cubed is what is equal to A. What's 1.65 cubed?
So 1.65 cubed. 4.24.
4.24? And now what's 29 divided by 4.24? 7. No, not quite. What is it?
6.4.
I'm sorry, what? 6.4?
6 point.
Okay. So now that we've solved for A and B, we know what our equation is. What should our equation be?
Equals 6.4 times 1.65 to the x.
Yeah, now it's important to understand that this A is never being taken to that x power. It's always only the B. And in fact, to be clear, I probably should put parentheses around it like that. And that is the form of an exponential equation. And you can get it by just, as long as you know for sure it's an exponential equation, then you only need 2 points to come up with it. Because there's only 2 variables, a and b. All right. Let me proceed. All right, I think I can do this without even talking about it. What's the well, I meant without me writing. On number 1, what's the domain?
-1 and 2 infinity.
Good. What's the range?
-infinity to 3.
Good. On 2, what's the...
-4 to infinity.
Okay, what's the range?
-3 to infinity.
And C, what's the domain?
-infinity to 2 and 2 to -infinity.
Brackets or parentheses next to the 2?
Parentheses.
Okay. And another way you could say it, I don't know if your teacher allows you to give multiple ways to describe range or domain, but on C you could say x is a member of all reals except x cannot be equal to 2. That'd be another way to describe the domain. I don't know if your teacher would accept that or if your teacher always requires it to be an interval notation. What's the range on C?
-infinity to infinity. Or
That's right.
-infinity to -1 and
Yeah.
-1 to infinity.
Now, to be fair, horizontal asymptotes can occasionally be crossed. There's definitely, you cannot cross a vertical asymptote, ever. But sometimes you can cross a horizontal asymptote. In other words, it's quite possible, I mean, obviously not in this graph, but you can have functions that do this. They cross the horizontal asymptote and then they're asymptotic with it, like that. And if I had something like that, then the range would be all real numbers. In other words, I would not have to exclude y equal -1. So just remember that horizontal asymptotes and slant asymptotes, I don't know if you've ever dealt with a slant asymptote or not, both of them can be crossed. They are not inviolable like vertical asymptotes are. What are you allowed to use to solve these? Are you allowed to use, is it just, you got to do it manually?
Probably use the calculator.
How come A is so difficult?
I have no idea.
Let me think about A for a second. Because, all right, how should we solve A? I was looking for an easy way. There's not always an easy way. If you can't figure out how to solve a quadratic, how should you solve it?
Quadratic formula.
Okay, let's get it. Hold on, let me take a picture of this. And so what's x equal? So
my -5 plus or minus 25 minus 4 times 0.3 times negative 3.2.
You see why I'm wondering why this is so hard?
Yeah.
Why did they make it with all these strange numbers? Well, there's the solution. And the rest is just arithmetic. I don't think you need help on arithmetic. You're really good on arithmetic. Okay? So we can solve that. And it's even a positive discriminant. So it's got real solutions. Let's not waste any more time on that. B, on the other hand, doesn't need us to use the quadratic formula. What is the solution for x?
15x. Well,
No, don't go backwards. You got it factored. Factored is how you want it.
0 and negative 1/3.
Okay. Now this one, I'm guessing, probably does factor. If it doesn't, we'll use the quadratic formula. But assuming it factors, what's my first step?
To add 2.
Now, does that factor?
Yeah.
Well, when I say that, does it factor nicely? Yes, you're right. It does, doesn't it? Okay. You can solve that one. You don't need answers. You don't need to turn this in, right? This is strictly for your review.
Yeah.
So I don't need to, once we've solved it, I can erase it. How about this one? You think this factors? Probably. If they meant us to use the quadratic formula on this, I don't think they would have given us A. How should we start to try to factor this?
2x and 2x.
Now can you see the problem? Plus plus. Only factors of 5 are 5 and 1. And that produces a gigantic middle term, which we don't have. We got 2x. Even if I try 4x and x, there's still no way I'm going to get as small a term as 2x. Therefore, it can't be factored normally, and we do have to use the quadratic formula on it. Again, we've gone through the quadratic formula enough times that I don't think you need more practice on that. How would you solve A?
You put negative 2x plus 4 into y in the first equation.
Okay, so by substitution. And again, it's always worth spelling it out without doing any math or simplification to begin with, just to make sure you get it perfect, which it looks like we did. Now, simplify it. Ooh, got a problem, don't we? Didn't solve for anything. What's the problem? What does that tell us? Tells us that the second equation is the same as the first equation. In other words, hold on. Man. In other words, when I get where I tried to do substitution and I got a number equals a number, that tells me that that second equation is probably the same as the first equation. It's not a different equation. Well, let's see. If I multiply both sides by 2, I get 2y equals minus 4x plus 8. I move the 4x over. I get 2y plus 4x equals 8. That's equation 1. This is not an independent equation. You don't just need two equations to solve a system of equations. You need two separate equations. So if you don't notice it, like we didn't, what ends up happening is you get a solution that's one number equal to another number. In other words, I was not able to solve for x, and I'm not going to be able to solve for y. The reason is I only have one equation. I might as well put a line through that. I got one equation. And when you have one equation and two variables, you have an infinite number of solutions. So that's the answer, infinite number of solutions to A. Now, let's try B. What system are we going to use on B? Are we going to use substitution or elimination?
Elimination.
Okay. What am I going to do first?
Times the first equation by -3.
So that gives me minus 9x minus 15y equals minus 27. That's my new equation 1. Now what?
You add them together.
Okay. So I get minus 13y equals minus 39. Y equals 3. How do I solve for x?
You put in 3 into y for any equation.
Any of the three, and almost never the new one that I wrote, because that's always got bigger numbers. In other words, personally, I'd go back and plug it into this one, because that's got small numbers and all positive. There's no negative numbers, and coefficient of x is a positive number, so it's going to be real easy to solve for x. All right. What if I have the following two equations? X plus y equals 10 and x plus y equals 9. Can you solve that system of equation?
Yeah.
Okay, do it.
I was gonna turn like one of the equation to y equals.
If I try just subtracting the two equations, I get 0 equals 1. That not only doesn't help us, but it's impossible. So that would be no solution. There's three different ways these can end. With an infinite number of solutions, like A, with no solution, like my problem, and with a specific, unique solution, like B. And they all going to end in one of those three ways. Now, the reason this has no solution is because it's really impossible. If you think about it for a moment, x plus y can be equal to 10, but it can't be also equal to 9. There's no way. If you think about what values of x and y might make both of these true, and there aren't any. There just is no way that both of these can be true. So it's no solution. All right. going to cover everything here, aren't we, by the time we're done with this document?
Hopefully.
Now I can see this is going to be a good review sheet. Alright. Let's take the one on the left. First of all, what's the parent function?
Square root of x.
I'm going to do that over here just because I need some room to draw it. And that function looks something like that. Okay? Starts at 0. X is never negative. Y is never negative. So what three things are going on with this transformed function that will allow me to graph it based just on its transformation? Start with the left. What's the 2 do?
Makes it,
and they want you to describe the transformation, so we need to use all the words. It's, first of all, is it a vertical or horizontal transformation?
vertical.
Okay, what is it? Is it a stretch or a shrink?
Stretch.
Or a shift? It's a stretch. It's unfortunate that all these words start with S, and some of them start with SH all. So it's a vertical stretch by 2, by a factor of 2. What about the plus 6? What is that? Horizontal or vertical?
Horizontal.
All the horizontals are inside the function, all the verticals are outside the function. What is this horizontal? Is it a stretch, a shift, a shrink, and which direction? What is it? It's a shift. Which way?
To the left.
By 6 units. And finally the minus 3. What is that?
Vertical shift down 3.
Vertical shift down 3. Okay, we've described it. State H, K, and A. What do they mean by H, K, and A?
The numbers on the equation.
Let's see. Name the parent graph. We've done that. Describe the transformation. We've done that. And then they say that, and I think what they're trying to say is, I'm not sure why they state it like that, but we've described the transformation completely with those three things. And somehow they mean H, K, and A to reflect these three things here. I'm not sure what they're talking about there. I'm not familiar with that terminology. Now sketch the graph. Well, sketching it is just following these directions, right?
Mm-hmm.
So I'm going to do my shifts first, because shifts, both horizontal and vertical, don't change the shape at all. So I can draw my shifts and draw the curve exactly like it looks like over here on the right. So if I go left 6 and down 3, where am I? Right there. That's my new starting point, and basically going to be exactly the same shape as this. Although that's without the vertical stretch. In other words, the only thing I've done is the horizontal shift and the vertical shift at this point. Now, the vertical stretch makes this curve look more compressed. It is going to double everything. So it's going to look like that instead of the black line. If I were to do strictly a vertical stretch, basically what the vertical stretch says is that any point that was on the black line is going to be twice as far away from the x-axis, right? I'm multiplying it by 2. So if I have a point here, the new point's going to be somewhere up there. And the net effect of all of those points is you end up with the green curve that I've drawn here, which is just a, I don't know how you want to describe it. You could kind of describe it as being horizontally compressed, which is the same as vertically stretched. Horizontal compression produces the same thing that vertical stretching does in the way that it changes the shape. So over here on the left, if I'm really trying to graph that entire thing, then I'm going to horizontally compress this thing, and it's going to look like that. Well, in fact, it's going to look something like that. Going through 0 in both cases. The vertical stretching does not affect going through 0. Alright. Let's talk about the curve on the right. We don't need to spend a whole bunch of time on it as long as you're comfortable with doing it. What's the parent function?
X squared.
Which I'll draw over here. What things do we have going on?
A vertical and horizontal shift.
Well, let's start from the left. And the reason we want to do that is because all reflections need to be done first. When you have a reflection as one of your transformations, then if you don't do it in the order of that, you'll get the wrong graph at the end. So the first thing we have is a vertical reflection. Now, what does that mean? The vertical reflection means what? Reflection over which axis?
The X.
Correct. You see why I call it vertical?
Yeah.
Okay. And you see why else I call it vertical? Is because everything that's outside the function is a vertical. Everything that's inside the function is a horizontal. Everything that's outside the function is vertical. So there's 3 vertical things you can do, and there's 3 horizontal things you can do. So if you tend to memorize it in terms of that, it makes it a lot easier to memorize these. Okay, the next thing, what's the 3 do?
Makes it bigger.
Vertical what?
Stretch.
By 3. What's the minus 3 do?
It's a horizontal shift.
Which way?
Or to the right, 3.
And finally, what's the plus 1 do?
Moves up 1.
Vertical shift, up 1. And so we could go through the exercise of graphing it. I suppose we should. In other words, let's do them one at a time. Let's do that first, and always one at a time, doing all reflections first. If you have 2 reflections, let's say you have a vertical and a horizontal reflection, you can do them in either order. but do all reflections before you do anything else. Once you do that, you can do them in any order you want. So the first graph I'm going to do is the reflection. Okay? Now, I'm going to do the reflection with a vertical stretch. Nah, you know what? Let's do our shifts next. Let's not do them exactly. Since I can do the rest of them in any order I want, the shifts are easier because they don't change the shape. And it's easy for me to draw a parallel curve. So in green, let's do this one next. The horizontal shift to the right. So I'm just going to put my new vertex there. It's going to look just like the same shape as my black curve. Okay. Now the next one I'm going to do is that. Up one. I'll do that in a different color. Again, same shape. And finally, I want to do this one, which is going to change the shape. It's going to stretch it. And every point on here, this red curve is going to be it's going to be 3 times as far away from the x-axis. So this vertex here that currently is at y equal 1, going to be up here. I don't want to do it in red. I want to do it in blue. So that point is there. This point is still right there, because when you stretch 0, you get 0. That point is still right there. So that part of the parabola looks like that. And then down below, this point here would be 3 times further away, so it would be down there. Same thing over here. So we're looking at a parabola that, whoops, meant to go through that. Anyway, you can see that it's been vertically stretched by an attempted factor of 3. I didn't quite get the factor of 3 right. But to me, that's the way to do those, is one transformation at a time. And if you have different colors, better yet. Makes it easier to understand. In fact, if you had different color pencils or ink and you're doing a test, this would be a great answer. I would love to see that answer from a student. That showed me that she did it one transformation at a time, and that he or she did the reflections first, not second or third. All right, let's see what we can do in 5 minutes. Let's take a look at C. I don't think we need to do D. What's the parent function on D?
Absolute value of x.
On D. We're not going to get to D, so I just want to check a couple things. What's the parent function?
X cubed.
Okay. Now let's go do C. Parent function is indeed, let me switch back to black. I'm going to graph that over here, just because. Okay. Now, how should I graph this function? You explain it, every step. First.
The vertical stretch of -2, so it's flipped.
So the first thing I should do is flip it. Okay, now what's the we can do, these are shifts, that's a shift. So why don't we do both of those next, and then we'll apply the stretch factor.
So you shift
Well,
to the left.
I know that it doesn't make a difference, the order. And the more I think about it, the more I think maybe it's easier to apply the stretch factor first. I think it is. I had difficulty applying the stretch factor on those others because they weren't at the center. Whereas here, if I apply the stretch factor first, it's just that. Okay? Now, all I got to do is take my green and apply the two shifts, and I'm done. So I'll do these both at once. What are my transformations? What's the +3 do?
Move it to the left 3.
And the -5?
Down 5.
Okay, so if I take my vertex here, go left 3 and down 5, there's the new vertex, and it's got the same shape as the green curve. So I think it does make more sense to do your shifts, your stretches and shrinks first, because I can approximate a stretch or a shrink of the parent function far easier than I can approximate a stretch or a shrink of a function that's been shifted and moved all over the place. You know what I'm saying? It's like if I wanted to do D, the first thing I'm going to do on D is this this shrink factor, and I know how to draw that almost perfectly. I don't have to do much estimation. I just got to change the slope by half. So I'm going to take back what I said earlier. I would do my stretches and shrinks first before I do my shifts. Now you still have to do the reflections first above all else. But the order I would always do it would be all reflections first, then all shifts or shrinks next, and then all shifts last. I'm sorry, all stretches or shrinks second, and all shifts third. That's the way to do it, I think. All right. Nicholas, I will talk to you tomorrow.
Okay.
All right? All right.
Bye.
Good night.